So we're going to do today more on quantum entropy. So remember that one useful definition classically was conditional entropy. You have two probability distributions x and y, or two random systems x and y, with a probability distribution p of xi and yj, and then sxy minus sy, we learned, measures what you don't know about x after learning y. So if you don't observe y, there's a joint probability distribution p of x and y, and an entropy sxy. If you have learned y, then you would assess, you'd have a conditional probability, p of xi assuming that y equals yj with the so, although this expression is just a difference of entropies, classically, although the formula looks like it's just a difference of entropies, it had the interpretation of the average entropy in the conditional probability distribution for x once you've measured y. We discussed that a few lectures ago, so we won't repeat it 1 week ago, I think, or 2 weeks ago, just before the break. We won't repeat it today. Now, one imitates this definition quantum mechanically. So now we have two quantum systems, A and B, and we define, this is usually denoted as conditional entropy of x given y, where the single bar means conditional on the second variable. So similarly, one defines quantum mechanically this difference as a conditional entropy. Although the formal definition is the same, the meaning isn't really the same, because there aren't conditional probabilities in quantum mechanics with the same properties as classically. So the classical expression, if you remember the derivation, we showed that this entropy difference, well, we got it as the sum of the average over y of the entropy of x given y equals yj. So classically, this expression was an average of ordinary entropies of a conditional probability distribution. As an average of ordinary entropies, it was manifestly positive. Quantum mechanically, it doesn't have an interpretation as such an average, and that's emphasized by the fact that in quantum mechanically, it can be negative. So to see that it can be negative, suppose AB is in a pure state, psi AB, then SAB is 0, but SB isn't 0, assuming that the state psi AB is entangled. As long as psi AB is not a simple tensor product, psi A tensor psi B, as long as it's not a simple tensor product, the density matrix rho B has rank bigger than 1. And so SB is positive. So this shows that SAB can be negative, in contrast to the classical case. It's maybe, at least at the elementary level of things we're discussing today, the most marked difference between quantum and classical. The quantum and classical case. Now, despite this, relative entropy quantum mechanically sometimes behaves similarly to the way it does classically. There's an example. If you read my article on the mini introduction to information theory, in the last section there's an example of that which is discussed, but I'm afraid we won't have time for it in these lectures. Now, another classical definition was the mutual information So the mutual information was defined as this difference. It's also the same as Sx minus S of x conditional on y. So since S of x conditional on y is what you don't know about x after learning y, and Sx measures what there was to learn about x in the first place, the difference is what you do know about x after learning y. And we, in the previous discussion, considered a couple of examples. For example, if p of x and y is a product, that means x and y are independent, and then you learn nothing about x by learning y, then the mutual information is 0, which you can check from this definition. The other extreme case is that y is just equal to x. If y is equal to x, then you learn everything about x if you learn y. And so the mutual information in that case is just Sx, whatever there was to learn about x in the first place. So again, we imitate this definition quantum mechanically. We say that the mutual information of system A between system A and system B is this entropy difference. But now this behaves better quantum mechanically. In a little while, we'll prove that this is always non-negative quantum mechanically, just as classically. You might remember that, I think in the previous lecture, we proved in formulas that the classical expression was positive. I think we did. But also the intuitive interpretation explains that it must be positive. We'll prove that the quantum version is positive in a little while. As always with quantum mechanics and as always in information theory, if all the density matrices are diagonal, the quantum story reduces to the classical story. So the proof we'll give of positivity in the quantum case actually has as a corollary the classical positivity. However, before proving that mutual information is positive, I'll explain a corollary. So we just defined the quantum mutual information, and we are going to discuss, we'll prove in a bit that it's positive, but first we'll explain a corollary. So you're given systems A, B, with some density matrix, rho AB. Remember, every density matrix can be purified. So we can assume that there's some quantum system C and some pure state such that rho AB is the associated density matrix for system AB, which means that it's the trace over C of the pure state density matrix. Well, another fact you remember is that, well, if you have a bipartite system, AB, which is in a pure state, then rho A equals rho B. So here, ABC is pure. So rho AB equals rho C. I'm applying this principle, but with dividing A, B, C into the subsystems A, B, and C. So because the overall state is pure, the two subsystems have equal entropies. So rho AB is C, and similarly, rho A is rho BC.
Do you mean entropy or actually density?
Ah, sorry. Thank you.
Okay.
Of course, the statement about the density matrices wouldn't make sense. They're matrices in different vector spaces. Thanks for straightening that out. So the fact that the overall system is pure gives these three relations. And now, we haven't yet proved positivity of mutual information, but we'll assume it for the moment. That gives that SA minus SAB plus SB is non-negative. And so SA is the same as SBC, and SAB is SC. So we learned that SBC minus SC is equal to or greater than minus SB. This was the entropy of B conditional on C. So remember, classically, the conditional entropy was non-negative. Quantum mechanically, it can be negative, but at least we have a lower bound, which is that it's not less than minus SB. And although we didn't prove it in class, I guess you will on homework. Okay, that reminds me, there is a third homework assignment, which is on my website, and probably Aaron will put it on Canvas. And if you're if you don't want to do the homework, please audit the class, because I want to pass everyone. It's a pass-fail course, but the way to pass you is that you do the homework. So if you're not doing the homework, please change your status to audit. Unfortunately, today was the wrong day to say that, because too many people are not here. Okay, so on a Hilbert, but anyway, an elementary result is that on a Hilbert space of dimension n, the entropy is equal to or less than log n. So we have a lower bound, which is minus the logarithm of the size of the Hilbert space of system B. So this formula is called the Araki-Lieb inequality. Araki and Lieb were pioneers of investigating quantum entropy in the 60s and 70s. So I've already explained a situation where this inequality is saturated. If SBC is 0, which is true if and only if rho BC is pure, then SB equals SC. And therefore, this inequality is saturated. And that's actually the only situation where it's saturated. Okay. Oh, okay. Any questions?
Sorry, there, so for that it's a one and then we have AB in a pure state, right? Because
No, AB was in any state.
is it, okay, so we were.
Let's go over the discussion again. So AB was in any state, rho AB. But any density matrix can be purified, meaning we can add another system. Okay. As I presented it, we started with being interested in systems A and B, but we proved the inequality about B and C. But the role of A, B, and C was completely symmetrical. We could have been interested at the beginning with B and C, and then we added A to purify it. Regardless of where the starting point was, we ended by proving this inequality, which is a rocky leap. Obviously, there's the same inequality with B and C exchanged. So we also have this. So therefore, it's often written as follows. That combines the statement I originally wrote and the corresponding statement with B and C exchanged. So yes, to resolve my confusion of about 10 minutes ago, we did in the lecture prove classically that mutual information was positive. We did so by first proving that relative entropy is positive, and then showing that mutual information was a special case of relative entropy. And that's what we're now about to do quantum mechanically. So the last basic definition classically was relative entropy so the relative entropy between x and y. So again, we have a probability distribution relative entropy of a single space x, but we have two different probability distributions, p and q. So one distribution is given by probabilities pi of x, or p of xi. The other is by q of xi. And then the definition was that the relative entropy of p to q was the sum of pi log pi minus pi log qi. And you might remember that we explained an example of its significance. If you have a hypothesis that a system is described by Q, but the correct answer is actually P, you can ask, after n trials, will you be sure that your original hypothesis was wrong? And the criterion for that is that when n times the relative entropy is large, you'll learn that your original hypothesis was wrong. How large it has to be depends on how sure you want to be that you were wrong before giving up on the original hypothesis. Now, quantum mechanically, one simply imitates this definition. So we have two systems, we have a single system A with two density matrices, rho and sigma. Then we define the relative entropy between rho and sigma to be the trace of rho times log rho minus log sigma. So you can see that if rho and sigma are diagonal matrices in the same basis, then the quantum formula immediately reduces to the classical formula. So, well, as I did say correctly 10 minutes ago, when we prove positivity of the quantum formula, there's a fallacy. When we prove positivity of the quantum formula, one of the steps is going to be that we already proved positivity of the classical formula. So it will not be an independent proof of the classical formula. Now, it's much harder to show this, but relative entropy has the same significance quantum mechanically as classically. Again, if you have a hypothesis that a system is described by density matrix sigma, and the correct answer is rho, you're given many identical copies of the system. For example, the system might be an atom. You have a theory that describes the decays of the atom. Possibly your theory is wrong, however. It predicts sigma as the answer for the final state, but the correct answer would have been rho. After observing n atoms, well, how big does n have to be before you learn you're wrong? The criterion is the same, but the proof is much more involved. I would have wanted to present it in this course, but I'm worried about running out of time for black hole thermodynamics, so unfortunately we won't. And we'll limit ourselves to, for the moment, we'll limit ourselves to just proving that S of rho relative to sigma is positive. So sigma we diagonalize. We diagonalize sigma in some basis. So sigma is a diagonal matrix, I guess. Okay. Well, sometimes I call it the eigenvalue cube, but it won't matter really. Now, rho is not diagonal. In the same basis. Let's let rho d be the diagonal part of rho. So we discussed this last time, and we observed that the diagonal part of a density matrix is itself a density matrix. If we drop the off-diagonal matrix elements of rho, we still have a Hermitian matrix that's positive with trace 1. So rho d is a density matrix, and we proved last time that the entropy of rho d is bigger than or equal to the entropy of rho. This inequality is strict if rho d is not equal to rho. Obviously, this inequality is saturated if rho d equals rho, but otherwise it's a strict inequality. So that's something that we proved last time. So once you know that, and also you know the classical positivity of relative entropy, the quantum positivity is straightforward to prove. We just add and subtract the term. All I've done so far is to add and subtract the trace of rho d log rho d. So the first two terms are entropies, S of rho d minus S of rho. Minus trace of rho d log rho d is S of rho d, and similarly for rho. And in the first term, over here we notice the following. Since log sigma is diagonal in the same basis where sigma is, the off-diagonal part of rho doesn't contribute in this trace. So here I can replace rho by rho d. And this then is the relative entropy between rho d and sigma. But that's a classical relative entropy because the two matrices are diagonal simultaneously. They commute. In other words, if we simply take the classical probability distributions given by the diagonal elements of rho d and sigma, this is the classical relative entropy between the two classical distributions. So this is non-negative, and it's strictly positive if rho d is not equal to sigma. And this is non-negative, and it's positive if rho d is not equal to rho. So if you combine the statements, you learn that S of rho relative to sigma is non-negative, and it's strictly positive if rho is not equal to sigma. Okay, any questions on this? Yes?
I have a question about the previous part.
Yes?
All right. So how do we interpret the fact that conditional entropy can be negative? I guess it's a quantum mechanics.
Well, the question is, how do we interpret the fact that quantum mechanically conditional entropy can be negative? It's very hard to interpret it intuitively, but that's part of the fact that quantum mechanics is hard to interpret intuitively. It shows dramatically, of course, that conditional entropy quantum mechanically is a formal definition. It's not the entropy conditional on anything. Entropies are positive, so if we really had entropies conditional on something, they'd be positive. The best I can tell you is that if I have a state that is totally entangled with some state you have, in some sense, I have more complete knowledge about your state than it would be possible to have classically, because I could make any measurement on my state. Let's say I could determine if it has spin up in the z direction, and then I would immediately know if your spin was up in the z direction, or I could do spin up on the x direction, or down in the x direction, or whatever. Anything I measured would enable me to predict a measurement on your state. It doesn't have an analog classically, of course. I'm not giving you an effective answer. I think it's an aspect of the strangeness of quantum mechanics. Okay. Negative conditional entropies are used in quantum teleportation, which I reluctantly decided I wasn't going to talk about in this course because, we have a limited number of weeks and we want to do black hole thermodynamics. Possibly if you read about that, it would give you a little bit of intuition about what negative conditional entropy means. Any other questions? So just as classically, positivity of relative entropy implies positivity of mutual information. And we can prove that by imitating the way we went from one to the other classically. So, in the classical proof, we started with a joint probability distribution, P of x and y. But then we defined another probability distribution where we ignored the correlations between x and y. So P of x is the probability of x regardless of y. Remember, it's defined by summing over y in P of x and y. Likewise for P of y. So P is the distribution we're interested in. Q is a distribution which has the same probabilities for x and y alone, but ignores the correlations. And then positivity of the relative entropy between those two gave positivity of the mutual information. Exactly the same thing works quantum mechanically. We have some rho AB of interest, but then we define a new density matrix, sigma AB, which is equivalent to rho AB if you're only going to measure A or B separately, but lacks the information that rho AB has about the outcomes of joint measurements of the combined system AB. What is the density matrix that does that? The density matrix that does that is simply rho A tensor rho B, where, of course, rho A is the trace over B of rho AB, and vice versa for rho B. So this partial trace operation was defined because it gave us the density matrix on system A, which is equivalent for measurements only in system A to rho AB. And likewise, rho B will give us the same outcomes for measurements of system B as you'd have in the density matrix rho AB. So sigma AB is the quantum analog of the product probability distribution, which predicts correctly the outcomes for observations of one system or the other, but doesn't give the correlations between them. In any event, now we can look at the positivity of relative entropy between rho and sigma and see what it says. Well, okay. So we have to calculate the logarithm of sigma AB. But with sigma AB being a tensor product, the logarithm of a tensor product is a sum. I guess the easiest way to convince yourself that this is correct is to check the, well, first of all, so after you convince yourself of this formula for the logarithm of sigma AB, we can put it in here. Now, one term is minus SAB. What about this next term with rho A? Well, B only appears in rho AB, and this expression is linear in rho AB. So we can just do first the trace over B. So you see, what we'll use is to find the trace over B of rho AB log rho A is just rho A log rho A. Oh, sorry. When I write rho A, I'm going to write this in a more fastidious fashion. It's rho A tensor 1. After you have a little practice, you'll make the same shortcut I was just making. But to write it out correctly for once, the fact which we're using here is that we have a matrix that acts on both A and B, and we want to take the trace over B, the partial trace. Well, the 1 doesn't really do anything, and the partial trace over B of rho AB will give rho A. So this is rho A log rho A. And likewise, the other one will give the trace of rho B log rho B. So we get SA plus SB minus SAB. So the mutual information was non-negative and strictly positive if rho AB is not equal to sigma AB, which is rho A tensor rho B. So we've proved that the mutual information is non-negative and vanishes only if the density matrix is a tensor product of density matrices of the two subsystems. So that's a close analog of the classical fact. So mutual information behaves more classically than conditional entropy does. Any questions on that discussion? Okay, I want to give another example, or an example, of positivity of mutual information. The example involves what's sometimes called a classical quantum density matrix. So we have a system that I'll call BC, and the density matrix, so the C system has a basis, let's say of n states. I'll call the general one I of system C. And the density matrix we want to consider is the sum over I of some probabilities pi times I projection operator of system C onto the state I, tensored with some density matrix, rho I of system B. So how would you get such a density matrix in the real world? Well, one possibility is that B is a system you were studying and C was a measurement apparatus. So a measurement apparatus is usually assumed to have a classical basis in which you read it. And the density matrix is assumed to be diagonal on the classical basis. And then you're supposed to know the state of the measurement apparatus in an undefined sense, not by measuring the state of the measurement apparatus. If you had to measure the state of the measurement apparatus, you'd get into an infinite regress. So Bohr simply assumed that you knew the state of the measurement apparatus in an undefined sense. And later authors, in my opinion, haven't improved on that. Okay, we could discuss that. For example, Everett supposedly eliminated the reduction of the wave function from quantum mechanics, but most people who say Everett did that haven't read his paper, I suspect. What Everett did was to say that you look at the measuring apparatus and then your brain records the value of I. So we have the bigger tensor product, let's say, which is I of the brain, tensor with I of the brain. And then according to Everett, you know the state of your brain in an undefined sense, not by quantum mechanical measurement. So Everett said the same thing about the brain that of the observer that Bohr had said about the measurement apparatus. Anyway, my purpose in saying this is to just orient you to why we would discuss this kind of density matrix. It's, well, it arises in analyzing the outcome of an experiment. And so, with that interpretation, C is the measuring apparatus and B was the experimental system. So the mutual information will tell us how much you learned about the experimental system by knowing the measurement. So now let's calculate the mutual information between B and C. So, okay. Well, it's a little hard to, okay. I want to write rho BC as a big matrix. So this matrix will have blocks corresponding to different possible states of the C system. Times anything of the B system. So one block is going to be just P1 times rho 1 of the B system. The next block is P2 times rho 2 of the B system. And the last one is pk times rho k of the B system. So the reason I did that is that I thought it makes it a little bit more obvious how to calculate the logarithm of rho CB. The logarithm of rho CB is block diagonal in the same way, but each block is a sum of two terms. There will be log of P1 plus the logarithm of rho B1. Then there's log of P2 plus the logarithm of rho B2, and so on. And then we can calculate SBC, which is minus the trace of rho BC times logarithm of rho BC. Well, it's a sum over blocks, of course. And in the ith block, from rho BC, we have pi times rho bi. Oh, we have to take a trace of all this. And then the logarithm, let's not forget that nice minus sign. Then the logarithm multiplies log pi plus log of rho bi. So since there were two terms in the logarithm, there are two terms in the sum. One term involves pi log pi. Because the rho b's, being density matrices, all have trace 1. The other term is a sum of pi times what? Well, the trace of minus rho bi times log rho bi. But that, by definition, is the entropy of rho bi. So one term in this entropy is the average entropy of the ith density matrix of system B, which you might remember is an average we said something about on Tuesday. And that's about to come up here. So we've calculated SBC, but we have to also calculate SB and SC. Well, we have to calculate rho B and rho C. So rho B is the trace over C of rho BC. Taking the trace over C means we don't care which state C is in. We just sum over all of them. So we sum all the blocks. So that's equal to the sum of pk times the kth density matrix of system B. But to get rho C, we take the trace over the B system, but the trace over each density matrix of B is 1. So the trace over the B system just gives a diagonal matrix with the probabilities of the C system. Well, so you see that S of rho B is the entropy of the average density matrix, the average of all these density matrices. Sorry. And what is S of rho C? Well, rho C has this nice diagonal density matrix, and its entropy is just the Shannon entropy of the probabilities of the measurement outcomes if the p's were measurement outcomes. So that's minus the sum of pk log pk, pi log pi. So now, if we calculate S of rho B plus S of rho C minus S of rho BC, you'll see that the Shannon entropies cancel out. And what we get is the entropy of the average density matrix minus the average of the entropies. And that we proved on Tuesday is positive by other methods. We've simply recovered that positivity from the positivity of mutual information in this situation.
Can you say what is the meaning of rho B? Is it the same matrix rho B or no?
We started with the density matrix rho BC. So we had a whole bunch of density matrices of system B. But what I called rho B was the reduced density matrix. Similarly, rho C was the reduced density matrix. So I tried to compute rho B over here. To get rho B, we have to take the trace over C of the joint density matrix. The joint density matrix is this one. And taking the trace over C means summing all the blocks. The blocks are labeled by which state system C is in. When we take the trace over C, it means we don't care. We just sum over those. So we just brutally add all the blocks. In this particular case, the partial trace just tells us to add all the blocks. So therefore, as I wrote here, rho B was the sum over I of all the blocks, namely pi times the ith density matrix of system I, a B, which is the density matrix system B is in if the measurement apparatus is in the state I. And for row C, we do the opposite. For row C, we take the trace within each block, thereby replacing each block with a number. The number is the trace of the block. Since each row B has trace 1, the partial trace over B gives for C a density matrix that's just a diagonal matrix whose eigenvalues are the probabilities for system C to be in its given state. So that's what we meant by row B and row C. And the mutual information is defined as S of row B plus S of row C minus S of row BC. And for this particular row BC, which is an idealized description of the outcome of a measurement, we computed the mutual information. We know in general it has to be positive, but we landed on our feet in the sense that we obtained an expression that we had proved by other methods was positive on Tuesday. Of course, the techniques that we used to prove it were also used today to prove positivity of mutual information. There's some redundancy between the different examples and arguments I'm giving, which is aimed at getting you more comfortable with the subject. Any other questions? Yes?
So the physical meaning of this mutual information is just how much information we can get from one physical measurement or from all physical
Well,
possible measurements?
well, when you say one measurement, so when we discuss classical information theory, we considered long messages. The analog of a long message is to have many measurements. So you might have many copies of the system, and you do measurements many times. But roughly speaking, it's how many bits of information you get by one measurement. So, okay. I can't think of a better answer to give right now. So, okay, let me just explain what's the problem with the question, though. In classical information theory, it's relatively straightforward to address a question like how many bits of information are involved in a given process. But quantum mechanically, arguments that justify statements like that are not straightforward and require much more sophistication than anything I've said so far. So, I think it's actually impossible to give that kind of answer, question a good answer, based on anything I've told you until now. Well, I'll come back to it in a little bit, maybe in about 15 minutes. We'll say a little more. Any other questions? So there's a much deeper statement. Sorry, before I get there. So just by way of terminology, the fact that this is equal to or bigger than 0 is called subadditivity of entropy. An example of what it's used for by mathematical physicists is this. Suppose you have a lattice system, like a quantum Heisenberg model, with spin-half particles on a lattice. Well, divide it into two pieces. I'll call them A and B. So SA plus SB is equal to bigger than SAB. Let's say that A and B have n spins, and AB has 2 n spins. And I'll also say that by symmetry, SA equals SB. Say the lattice has translation symmetry, and we can assume the quantum state of the lattice respects that symmetry. Then you could write the inequality by saying that S of n spins divided by n is equal to bigger than S of 2n spins divided by 2n. Of course, you could iterate this and next look at S of 4n spins divided by 4n, and then 8n spins divided by 8n. So you learn that as you approach the thermodynamic limit, the entropy per spin can only go down. However, the entropy is bounded below by 0. So it has to approach a limit. So this proves we did assume translation invariance, but if you know that your lattice system has translation invariance, this proves that the entropy per spin has a thermodynamic limit. So that's why, well, as I told you, Lieb in this department was one of the pioneers of quantum entropy, and this is probably an elementary illustration of the kind of thing that some of these things are used for. But there's a much deeper property. So this is called subadditivity of entropy. There's a much deeper property which is called strong subadditivity. Actually, first proved a little, I think, over half a century ago by Lieb and Rescalli, and also generalized by Ullmann. It's extremely important in many applications. I'm going to give a kind of explanation of why it's true, but not today. That will be after we have done some more quantum field theory. But for today, I'm going to only explain that it's the corollary of another deep statement, which is called monotonicity of relative entropy. So monotonicity of relative entropy says the following. We have two systems. Well, we actually proved the classical version last week, so let me remind you of the classical version. We have a bipartite system, xy, and we have two probability distributions, qxy and pxy. And then we can also define reduced probability distributions, px and qx, gotten by summing over y, the classical analog of the partial trace. And then we proved that the relative entropy of px relative to qx was no bigger than the relative entropy of pxy relative to qxy. So we proved it with formulas, but we also gave the intuitive interpretation. The intuitive interpretation, so Q is your hypothesis, but maybe it's wrong. P is correct. And we want to know how much data it will take before we prove that the hypothesis was wrong. It's easier to prove the hypothesis is wrong if you have access to observations of both x and y rather than only x. The right-hand side measures how well you can do if you measure both x and y. The left-hand side measures how well you can do if you only measure x. So that led us to expect this inequality, and I think we proved it with a little manipulation involving logarithms. So the classical quantum analog is that you have a bipartite system AB, and you've got rho AB and sigma AB, two density matrices. Maybe sigma is your hypothesis, rho is the correct answer, and you're trying to distinguish them. And monotonicity of relative entropy is the statement that the quantum inequality also holds. So it's also true quantum mechanically that relative entropy measures how hard it is to disprove a hypothesis. So this formula has the same intuitive interpretation it has classically, but it's much longer to prove that. At the end of the course, if we get tired of black hole thermodynamics, maybe we'll do that, but I suspect we won't get there. You'll have to read about it on your own if you want to. But we will give a kind of quantum field theorist explanation of this statement, but not for a few more lectures. For today, we'll just discuss the corollary. The corollary is strong subadditivity. So now we consider three systems, A, B, C. So we have a density matrix rho A, B, C. But there are various reduced density matrices we can define. So for example, we can define rho AB, which is the trace over C of rho ABC. We can also define rho C, which is the trace over AB of rho ABC. And various others. Now, where did I put my notes? So here we're going to define a new density matrix, sigma ABC. Equal rho A tensor rho BC. So, rho A, of course, is the trace over BC of rho ABC. And similarly for rho BC. So sigma ABC has the same predictions that rho ABC has for observations of only A or observations of only BC. But if you make joint observations of the two systems, then rho has more information than sigma. Now we could also, of course, or we can forget the C system. So that means we replace rho ABC with rho AB, which is the trace over C of rho ABC. And we can do the same thing to sigma. Well, that would be the trace over C of sigma ABC, but sigma ABC is rho A tensor rho BC. So that is simply rho A tensor rho B. So now we're going to apply, we're going to use monotonicity of relative entropy for the systems A, B, and C, I think, and the density matrices rho AB, C, and sigma ABC. So maybe I should, okay. So maybe I should call it ABC and AB. So we could look at the relative entropy between rho AB and C and sigma ABC on the full system A, B, and C. Or we could take a partial trace over C and just look at the relative entropy on AB. So this statement here we're going to use with A replaced by AB and AB replaced by ABC. So we have S of rho AB relative to sigma AB is equal to less than S of rho ABC relative to sigma ABC. Well, on the left-hand side, since sigma AB is rho A tensor rho B, as I must have written somewhere on this blackboard, I guess. Yeah, here it is. Sigma AB is rho A tensor rho B. So the left-hand side is the relative entropy of rho AB relative to rho A tensor rho B. And we just calculated in our discussion of positivity of relative entropy that that's SA plus SB minus SAB. The right-hand side well, by definition, it's the relative entropy of rho ABC to sigma ABC, but sigma ABC was defined as rho AB tensor rho C. So we can use this same fact again, but with A replaced by AB and B replaced by C. This is then SAB plus SC minus SABC. So our inequality says that SA plus SB minus SAB is equal to less than SAB plus SC minus SABC. Oh, sorry. Something's gone wrong. Thank you. That was in the nick of time because thank you very much. I was about to notice that I was writing down an incorrect conclusion. Okay. So the correct right-hand side is SA plus SBC minus SABC. So we can slightly simplify it by canceling the SA, and we can write it in the form that's most often written, I guess. So this is called strong subadditivity. We didn't prove it, we just showed it was a corollary of positivity of relative entropy, which is something we will discuss later in a couple lectures. Any questions on that discussion? So there's a variant which is illuminating. So we had systems ABC with rho ABC. But we know we can purify any density matrix. So there's some additional system D and some pure state psi ABCD such that rho ABC is the trace over D of the pure state density matrix. And then remember that if you have a remember that in a bipartite system in a pure state, the two entropies are equal. So for example, in this state, SA equals SBCD, SB equals SACD, SAB equals SCD, etc. In other words, if I take the four systems A, B, C, and D and split them into two groups in any fashion, since the overall state is pure, the entropy of one half is the same as the entropy of the other half. So I can split A, B, C, D into A together with B, C, D, and their entropies are equal. Or I could split it into A, B together with C, D, and their entropies are equal, and so on. So I can do this to this inequality, and I'll do it in such a way as to get rid of system A. So wherever A appears, I'll use this principle to get rid of it. So I'll say that SABC is SD, and SAB is SCD. So then the inequality becomes SB plus SD Sorry, I think that's not what I'm going to do. I'm going to get rid of A and B both in favor of C and D. So I'll use the fact that SABC is SD, but then I'll replace SAB with SCD. The inequality becomes SB plus SD equal to or less than SCD plus SCB. Or in other words, I could write it in the form SBC minus SB plus SDC minus S. According to my notes, what we're supposed to get is we're supposed to get SD. Oh. Yeah, okay, that's right. Fine. So this is the same as the sum of two conditional entropies. So remember, conditional entropy was positive classically, but it's not positive quantum mechanically in general. But here, the rather deep statement of strong subadditivity, which I repeat again, is much deeper than anything else I've told you about entropy, implies that this sum of relative entropies is non-negative. Now, the intuitive meaning is what's often called monogamy of entanglement. System C could be entangled with system B, causing this to be negative, or it could be entangled with D, causing this to be negative, but it can't be entangled with both. Well, let's check the inequality in a simple case. Let's suppose that BC is in a pure state, and D is in any state. So rho BCD is some pure state of system BC tensored with some state of system D. Well, if that's the case, SBC is 0. Well, for simplicity, we could assume that this is maximally mixed state. If it's maximally mixed, then rho C is just a multiple of the identity. Let's suppose our systems are qubits, two-dimensional Hilbert spaces. Then SC is log 2. SD is something. And the one other term in the inequality we have is DC. Well, rho CD is just a product. Rho C tends to rho D. So SCD is log 2 plus SD. I didn't really have to assume that SC was log 2. It could have been anything. It would have canceled out of this inequality. Anyway, if B and C are entangled and uncorrelated with D, that's an example where this inequality is saturated. But instead of getting into the formulas, I should have given you the idea. A quantum system can be entangled with something else, but it can't be simultaneously entangled maximally, let's say, with two different things. So if system C is entangled with B, that reduces SB, but it increases as entanglement of C with system B will make this one go down, but it makes this one go up. And the inequality says that one goes up by at least as much as the other goes down. So this puts some limit on how much we can get negative conditional entropies. I think I slightly garbled that explanation, but we'll have to live with it. So it's more or less time to call it quits for today, but I'll stop here for questions, if there are any. Okay, well then we'll finally get to quantum entropies and generalized measurements on Tuesday, and then we'll start discussing the thermofield double state, and we'll go back to quantum field theory.